лекции Дэвида Кринга, прочитанной в прошлом году, 11 июня 2016 года, затронут вопрос рождения Луны, которое произошло 4,5 миллиарда лет назад. Лектор рассказал о гипотезе ударного происхождения Луны. Он продемонстрировал симулятор Робина Канапа, где видно, как из осколков Земли и налетевшей на нее небольшой планеты образовался аккреционный диск, из которого довольно быстро, в течение 1000 лет, сформировалась Луна. Сначала она была в 16 раз больше, чем сегодня, и находилась на расстоянии 3,8 лунных радиусов. Затем, 3,9 миллиардов лет назад Луна существенно уменьшилась в размерах и удалилась от Земли на расстоянии 21 лунного радиуса. Сегодня она имеет еще меньший диаметр и находится от Земли уже на расстоянии 60 лунных радиусов. Итак, Дэвид Кринг придерживается принятой сегодня точки зрения на рождение Луны, которая окончательно сформировалась 5 лет назад в недрах Гарвардского университета. Впервые об этой гипотезе заговорили в 1974 году. Ее сторонники называли свое детище гигантской или большой теорией столкновения. Они утверждали, что 4,5 миллиарда лет назад Земля столкнулась с объектом, равным приблизительно сегодняшнему Марсу. Это столкновение дало множество осколков, которые начали вращаться вокруг Земли. Робин Кеннеп создала компьютерную модель для изучения деталей сценария удара. Через 10 лет, в 1984 году, на лунной конференции на Гавайях, ведущие астрономы мира, в основном, достигли консенсуса в том, что теория Канапа наиболее приемлемо объясняет происхождение Луны. Вторым важным моментом предыдущей, 95-й части конструктивного познания является акцент, сделанный специалистами НАСА в программе пилотируемых космических кораблей «Аполлон», начиная с 11 номера и кончая 17-м. Этот акцент указывает на ударное происхождение кратеров и вообще, всей Луны в целом. Именно поэтому эту теорию назвали гигантской или большой импакт теорией. Существовало несколько моделей возникновения Луны, но сегодня официально признана одна, которую разработал Робин Кеннеп. Победа ее теории как раз и объясняется тем, что с помощью одного большого удара удалось убить сразу двух зайцев, то есть найти причину для возникновения самой Луны и причину для возникновения множества ударных кратеров на лунной поверхности. Таким образом, кратеры на поверхности Луны возникли не от падения первичных метеоритов из пояса астероидов, расположенного между Марсом и Юпитером, а от падения так называемых вторичных метеоритов, которые появились в результате столкновения Геи, то есть древней протоземли, с Теей, то есть с планетарным объектом размером с Марс. Сейчас мы покажем короткий фильм, где рассказывается история данного вопроса.
The Earth, over its 4.5 billion year history, has been pummeled by asteroids. Eroded by wind and rain. Covered over with flowing lava. Wrinkled and gouged by shifts in its crust. Most traces of its distant past have long since been destroyed. But there is a place where clues to the early history of our planet are still largely intact. The Moon. Scientists have been reconstructing its history by scouring its surface, mapping its mountains and craters, and probing its interior regions. What are they learning about our own planet's beginnings? By going back in time to the mysterious birth of the moon. The space age made possible rockets with enough power to blast humans and their life support systems into orbit. More than 300 manned space flights have shown that humans can live and explore beyond our Earth.
Differentiate me from Dr. Feustel's suit right here, which has red stripes.
None of these missions have done more to shape our connection to the cosmos and define who we are than the fabled flights of Apollo. But not for reasons you might think. We sent astronauts to the moon as a symbol of confidence in the face of the great Cold War struggle. Many hoped that would lead to further journeys to Mars and to an age of living in space. Those goals proved too grand in the face of all the preoccupations, turbulence, and change that would crash onto our own planetary shores. Landing on the moon was a giant leap for mankind. But it's what the astronauts picked up from the lunar surface that may turn out to be Apollo's greatest legacy. When the astronauts of Apollo stepped out of their landing craft, they entered a world draped in fine, sticky dust, strewn with rocks and pocked with craters. They walked and rambled about, picking up rocks, 382 kilograms worth, that they packed for the return flight. Back in Earth-bound labs, scientists went to work probing the rocks for clues to one of the most vexing questions in all of science. Where did the moon come from? The answer promised to shed light on an even grander question. Where did Earth come from? And how did it evolve into the planet we know today? The Apollo rocks have brought us closer to the answer, but basic mysteries still remain. The moon orbits Earth at an average distance of 384,400 kilometers. It's relatively small, with less than 1% the surface area, 2% the volume, and 1% the mass of Earth. With no atmosphere, temperatures range in Celsius from minus 233 degrees at night to 123 degrees during the day. As the brightest object in the night sky, the moon has guided people for millennia by defining the rhythms of life and animating our myths. The nature of the moon began to come into focus 4 centuries ago. Galileo Galilei had heard of an instrument built by Dutch opticians capable of seeing faraway things as though nearby. Galileo, in many ways the first modern scientist, saw this new instrument as a tool to help settle a long-standing question. What was the nature of the heavens, and how did the world of men fit within it? To some philosophers, the moon was a perfect crystalline sphere of divine substance, free of Earth's imperfections. Galileo, with his telescope, saw a more familiar reality. He noted mountains and valleys on the moon, features like those of Earth. Flash forward to the modern age of lunar studies. 1959 saw the first in a fleet of probes launched by the Soviet Union and the United States to shoot close-up pictures, take readings, and crash onto its surface. We learned then just how different the moon is from Earth, with its cratered and desiccated landscapes and lack of a magnetic field. That intensified a debate about the moon's origin that went back centuries. The so-called fission theory, championed by George Howard Darwin, son of Charles Darwin, held that the moon was once part of the Earth, cast off by the rapid spin of its young parent. For proof, look no farther than the Pacific Ocean, a giant hole in the Earth's surface. Then there's the capture theory, which holds that the moon was a wayward object that floated through our solar system and was pulled into orbit by Earth's gravity. A third idea came from the American astronomer Thomas Jefferson Jackson C., also known for his attacks on Einstein's theories and for charges of plagiarism that were leveled at him. He suggested that the moon formed near Earth and gradually fell under its gravitational spell. In that case, the moon should be a mini-Earth, which we now know it's not.
Bypass across the board, Scooter, no action.
The astronauts of Apollo lifted off on a series of missions to get a close-up look at the moon and perhaps settle the debate. Because there's no atmosphere there, the astronauts entered landscapes that are nearly frozen in time. They could scour the lunar surface for evidence of events going back almost to the time of its birth. Indeed, eons of impacts had opened up the moon's interior, leaving a wealth of information strewn about their landing sites. Scientists had already noticed that some large old craters were surrounded by concentric rings. You can see one of the most pronounced examples in this image of the Mare Orientale, captured recently by NASA's Lunar Reconnaissance Orbiter, or LRO. The colors showed differences in elevation. The old view was that the impact had melted the rock below. A newer view held that the impactor had actually splashed down on a molten surface. That gave rise to the radical notion that early in its history, the moon's surface was covered in a vast ocean of magma. When the astronauts arrived, they found relatively light rocks known as anorthosites. Their presence suggested that heavier material had sunk toward the moon's interior, forcing lighter material to the surface. The rocks they brought back were found to be strikingly similar to those on Earth, in part because they share forms of oxygen, called isotopes, that scientists regard as blood types for solar system bodies. Then there was this. The moon appeared to be completely, utterly dry, with no evidence that water was ever present on its surface. Not long after the last Apollo mission went into the history books, this initial evidence coalesced into a radical new idea, first presented in 1974 by the scientist and artist Uильям Хартманн. His theory of the moon's formation is played out in this contemporary scenario. Sharing an orbit with Earth, was a Mars-sized body called Theia, named for a Titan in Greek myth who gave birth to the moon goddess Selene. Its orbit became unstable, and it headed in Earth's direction. Theia hit at an oblique angle, causing the Earth to spin faster, and debris from both Theia and the Earth to fly into orbit. When the dust settled, the debris began to coalesce in Earth orbit, forming the Moon. By then, volatile compounds like water had evaporated. The Moon, then, comes primarily from the mantles of the Earth and Theia. That's why, overall, the Moon is lighter or less dense than Earth. It has a core of solid iron like Earth, but this core is relatively small compared to ours. From this violent beginning, the Moon gradually cooled, and the magma that lined its surface hardened into a crust. Yet it was still subject to intense bombardment in the chaotic environment of the early solar system. Its surface has been hammered by large impacts at every stage in its history. You can see what a battering the Moon has taken in this global elevation map compiled by the Lunar Reconnaissance Orbiter. The Apollo astronauts encountered a secondary effect of all the impacts. Rocks formed in the crucible of widespread volcanism. On Earth, volcanic eruptions are often powered by water, heated and pressurized by friction from the movement of immense tectonic plates. Neither factor exists on the Moon. Instead, lunar volcanoes are tied to impacts, forceful enough to melt the surface and release material from the hot interior. Molten rock then flowed out in thin, smooth layers that reached far from its source. That's how the mare regions, that cover about 1/6 of the entire lunar surface, were formed. These immense volcanic basins are thought to date back to a period of large and violent impacts from 3 to 4 billion years ago. The materials brought up by these impacts are made up of heavier compounds that would have initially sunk into the magma ocean. Scientists have also detected volcanic residues in recent impacts that have been imaged by LRO cameras. This is the Aristarchus Plateau, with a mysterious channel cut by flowing lava and punctuated by 2 immense craters. One was created by an impact just 450 million years ago. Along its walls are blocks of rock from the lunar crust that fragmented in the impact. Scientists detected volcanic glass-like deposits that are the legacy of ancient eruptions. Then there's the strange landscape of the Tycho crater, from an impact about 100 million years ago. Its central peak, rising 2 kilometers above the crater floor, may be material blasted out by the impact. The same is true for a 120-meter wide boulder that sits on the summit. Around it and on it, scientists see evidence of rock that was melted in the heat of the impact itself. Since its birth, the Moon has exerted a constant and powerful influence on Earth. Gravitational drag from the Moon slows Earth's rotation by 2.3 milliseconds per century, while causing the Moon to drift away at a rate of 3.8 centimeters per year. The Moon's tidal pull acts to stabilize Earth's rotation about its axis, and the tides help promote the formation of ocean currents that shape our climate. To think that the root of this intimate relationship between Earth and the Moon stems from a violent collision so long ago. However, the giant impact theory is not universally accepted. For one thing, there's the issue of water. The dryness of the Moon is consistent with the giant impact theory, which predicts that water and other volatile compounds would have evaporated out of the lunar debris cloud. But the Moon may not be so dry after all. In 1998, the unmanned lunar prospector began an ambitious mission to map the lunar surface with an instrument called a gamma-ray spectrometer. The data showed that hydrogen is spread widely across the poles of the Moon. If it's from ice, millions of tons of water could well be embedded in the soil there. It turns out there are places where water can exist on the Moon, where the sun never shines. Polar craters forever in shadow could shelter significant quantities of ice against solar radiation. Prospecting for ice, the L-Cross probe arrived at the Moon in 2009 aboard the Lunar Reconnaissance Orbiter on a collision course with the 97-kilometer-wide Cabeus crater at the South Pole. Seconds after it slammed into the crater, a trailing probe detected a tenuous cloud rising up from the crater. In the cloud was a mix of carbon monoxide, ammonia, methane, and more. 5.6% of the crater floor is water ice, a higher concentration than some areas on Earth. The presence of water is good news for explorers who dream of one day spending quality time on the Moon. But how did it get there? It might have been delivered by comets striking the Moon over the eons. There's another explanation, one that emerged from rocks gathered by the Apollo astronauts. The samples are graced with tiny glassy globules, minerals melted in the crucible of lunar volcanism. Analyzing these Apollo rocks with new techniques, several teams of scientists have found a compound called hydroxyl. It's H2O with only one H, and could be turned into water, say, for a moon base. Much of what the Moon had was likely lost to space from impacts. Tiny residues might remain in polar craters. The rest, still locked up inside the Moon, might be enough to cover its surface in a layer of water 1 meter deep. Does the presence of water inside the Moon send us back to square one on its formation? It might not, if it had been carried in by comets in the Moon's early days. One new study suggests that the giant impact scenario is more complex than we thought. It holds that another, much smaller body formed alongside the Moon and eventually merged with it. The impact literally rearranged the moon's interior, pushing molten magma onto the near side, while adding an extra layer of crust to the far side. That explains the lopsided topography of the moon, the dark lava basins on the near side, and the highlands of the far side. Human geologists with a network of seismographs could confirm this idea. The next best thing is a mission called GRAIL, a pair of spacecraft orbiting the moon in unison. Such a mission has already performed a kind of planetary CAT scan of Earth. By measuring subtle changes in the distance between the craft, scientists discerned variations in Earth's gravity. The data resulted in a map of groundwater all around the planet. Flying around the moon, the GRAIL pair could provide new details about the size and composition of the moon's core, adding support for the giant impact theory, or sending science in a whole new direction. The intimate connection between the Earth and the Moon appears to trace back to their earliest times. If that's true, then the formation of this desolate world can tell us about our own. A blue-green world with a companion reflective enough to light up the night.
У нас в стране, да и за рубежом, есть немало скептиков, которые не верят в факт высадки американцев на Луну. Эти выводы они делают на том основании, что на широко распространенных фотографиях не видно звезд на черном небосводе. Задаются язвительным вопросом, как может развиваться американский флаг, когда известно, что на Луне отсутствуют атмосферы и не дуют ветры. На только что показанных документальных кадрах вы можете оценить плохое качество киносъемки, которое не позволяет рассмотреть звезды. Разумеется, помещенные в интернете цветные, очень качественные снимки сделаны в студии. Американцы гордятся своими инженерно-космическими достижениями и вкладывают огромные суммы денег в пропагандистские материалы, предназначенные в основном для детей и обыкновенных обывателей.
For those who haven't read the plaque, we'll read the plaque that's on the front landing gear of this LEM. There's two hemispheres, one showing each of the two hemispheres of Earth. Underneath it says, "Here men from the planet Earth first set foot upon the moon, July 1969 AD. It came in peace." I guess you're about the only person around that doesn't have TV coverage of the scene. That's all right, I don't mind a bit. How is the quality of the TV? Oh, it's beautiful, Mike. It really is. Oh, geez, that's great. Is the lighting halfway decent? Yes, indeed. They've got the flag up now, and you can see the stars and stripes.
Естественно, эти документальные съемки очень неважного качества не идут ни в какое сравнение с цветными съемками, сделанными в студии Голливуда. Но давайте, наконец, переходить к сути нашей проблемы. Она заключается в ошибочности принятой на сегодняшний день гигантской импакт-теории. Почему теория ошибочна? Наш конструктивно думающий зритель, наверное, догадался сам. Разве не видно, что вместо адекватной модели, отображающей естественные процессы в замороженном эфире, нам подсунули взрывную искусственную модель, то есть некое придуманное явление, навеянное людьми с катастрофическим образом в голове. Это чисто программный продукт, который не заслуживает даже названия модель. Лучше всего к нему подходит слово «симулятор» в прямом русскоязычном толковании. Мы видели симуляторы гравитационных волн и симуляторы черных дыр, а также множество других симуляторов, о которых не станем сейчас говорить. Лучше обратим внимание на характер лунных кратеров, в частности, на хорошо известный кратер Тихо. Ведь это типичный кратер Мар, когда дно кратера, оно синего цвета, находится ниже окрестностей, окрашенных в зеленый цвет. Авторы неправильно интерпретируют свечение так называемых лучистых кратеров, о которых уже говорилось и будет сказано в будущих частях устройства Солнечной системы, поскольку лучистые кратеры есть не только на Луне, но и на множестве других космических объектах. Спутники Юпитера и Сатурна, спутник Плутона Харрен, астероиды Церера и Веста, все они имеют лучистые кратеры, которые свидетельствуют о внутренних напряжениях в объектах-носителей этих лучистых кратеров. Длительное свечение отдельных участков в районе кратера не порождается ударом камней. Оно вызвано пьезоэффектом, ионизирующим частицы, которые начинают светиться под действием прямых солнечных лучей. Сейчас мы покажем два фильма о работе американской исследовательницы Робин Кеннеп. По-видимому, на сегодняшний день она является самым востребованным специалистом по Луне и другим спутникам Солнечной системы. О ее модели рождения Луны рассказывал Дэвид Кринг, о чем мы говорили в самом начале этой, 10-й части устройства Солнечной системы. Итак, смотрим.
I think it was the hairdo that really did it. To years of ballet lessons as I pursued the dream of becoming a ballet dancer. Ultimately, I came back to science, and it was at Duke University that I was really inspired by two amazing professors, John Kalina in astrophysics and Horst Meyer in advanced physics lab, and they really inspired me to pursue graduate studies. My thesis advisor, Larry Esposito, started me on models of planetary ring dynamics, and then was very supportive when I decided halfway through my thesis that I wanted to change topics and work on the origin of the moon instead. I'm forever grateful to him for that because it's been a topic that I've been interested in ever since. Soon after I got my PhD, I joined what was then a small remote office dedicated to planetary science of the Southwest Research Institute. Southwest is a nonprofit, private institute based in Texas. The planetary group in Boulder has grown greatly ever since, and it's a wonderful and supportive environment to conduct planetary research. It was at Southwest that I met and started working with Bill Ward, who has been my closest scientific collaborator now for the past 15 years. And finally, and most importantly, I'd like to acknowledge the love and support of my family, my husband Rick of the last 20 years, and our children Natalie and Asher. So I'm going to talk about the formation of the primary moons in our solar system. These are a highly varied group of objects, and we think their origins are tied directly to the origins of the planets. I'm going to start with a plot showing very basic properties of the satellite systems. So I'm plotting the mass in the satellite system, ratio to the planet's mass, as a function of the radial scale of the satellite system shown in planetary radii. And on this first plot are the satellite systems around the solid planets and the dwarf planets that we now know exist in the outer solar system beyond Pluto. These systems show a wide diversity on this plot, ranging from tiny satellites of Mars all the way up to the relatively quite large satellite of Pluto. In stark contrast are the satellite systems around the gas giant planets. They are closely clustered on this plot. This is because they each contain a nearly identical fraction of their central planet's mass, about 10 to the minus 4. And this similarity is very surprising because we think that each of these planets would have grown by quite different circumstances. So the fact that they share this property we think is a real clue to their origin. So I'm going to talk about two different mechanisms for forming satellites that we think may be able to explain these two very different distributions. In the cases of the satellites around the solid planets, we think they may have formed from giant collisions. And for the satellites of the gas planets, we think they formed within gaseous disks around those planets as the planets formed. So the idea that an impact could produce a satellite was first really developed for the origin of our moon. The idea is that the Earth was struck by another planet-sized object as it finished its formation. The giant impact theory, as it's called, is favored because it does a good job of explaining most of the basic properties of the Earth-Moon system. For example, the moon raises tides on the... Okay, I'll put this down while I'm talking. The moon raises tides on the Earth, and the interaction of the moon with these tides causes the moon's orbit to expand over time and the Earth's rotation to slow. From this, we know that when the moon first formed, it was close to the Earth, and the Earth was rotating much more rapidly, with only about a 5-hour day. So an off-center collision by a large planet is a natural way to explain how the Earth got this fast initial rotation. In addition, we know from the moon's bulk density, it's strongly depleted in iron compared to the Earth, and as I'll show you, a giant impact can also explain this. And finally, we think these large collisions were common during the final stages of assembly of the inner solid planets in our solar system. So to model these types of events, we use three-dimensional numerical simulations. The ones I'll show you represent the colliding bodies by a multitude of particles, typically 100,000 or so. And you track the individual evolution of each particle as it evolves due to gravity and pressure forces. And an input equation of state then tells you how each particle's material responds thermodynamically to the impact, whether it melts, vaporizes, and what its temperature is. So I'll show you some animations of a potential moon-forming impact. Here the color is scaling with temperature. So 2000 K is represented in blue. That's molten silicate, whereas the red particles that you'll see at low pressure are vaporized silicate. So here the Earth, the lower left, is being struck by a Mars-sized impactor on the upper right. So the initial impact, pause it here if I can, destroys the impacting object. After a few hours, in this case, the inner portions of the impactor actually coalesce into a clump that re-impacts the Earth. There's another large clump out here that you'll see makes a very close pass by the Earth here. And as it gets very close to the Earth, Earth's tides strip it apart, and this material provides most of the mass in what is a disk around the Earth after this simulated 24-hour period. So we have a rapidly rotating Earth surrounded by a disk with enough mass to later accumulate into our moon. So this is the same impact with a different color scheme. Here the color corresponds to material type. And you can see that we're assuming that both objects initially have large Earth-like iron cores. Because of the geometry of the impact, the iron core of the impactor collides more directly with the Earth. And as that inner clump of impactor material collides with the Earth, it contains most of the impactor's core, so that as it collides with the Earth, most of the iron is removed from the disk. So that in the end, the disk has only a few % iron by mass, and that's consistent with the amount of iron that we believe is in the moon. So this is the last animation of that same collision. This one is in 3D, and in particular, you'll see that the most strongly heated material at the initial impact site, those are the red particles, will wrap itself around the planet and form a silicate vapor atmosphere around the Earth. Okay, there's the initial collision. Here are these vaporized particles wrapping around the Earth. This is the iron core of the impactor coming in for that secondary impact. as the simulation progresses, our viewing point is moving. And so we're now going to move into the plane of the disk. So we're looking at the planet on edge. You can tell it's very oblate. That's because it's rotating so rapidly with a day of only about 5 hours in this case. And now we're going to be looking from underneath the planet. There's that outer clump that gets stripped apart. So this collision has been optimized to produce a disk capable of producing our moon. But if you consider different types of impacts, you can produce very different types of disk. And in some cases, you can even form an intact satellite directly from the impact itself. This is a type of collision that can produce a Pluto-Charon-like pair, where the satellite is very massive compared to the Earth. So using lots of these simulations, one can find that a wide range of satellite system properties can likely result from these impacts. Each of these points are results from one of the impact simulations like the ones I've shown. So in general, we think we can explain the diversity of solid planet systems from these giant impacts. So let me turn now to the origin of the satellites of the gas giant planets. I'm going to focus on the satellite systems of Jupiter and Saturn. Around Jupiter, of course, we have the 4 famous Galilean moons. They're each similar in mass to our moon. If you combine their mass and ratio to the mass of Jupiter, the system contains a mass ratio of 2 times 10 to the negative 4. At Saturn, we just have one large satellite, Titan, and Titan contains more than 95% of the mass in the satellite system. Saturn also has a massive, essentially pure ice ring system that distinguishes it. But despite the fact that this system looks very different from the system at Jupiter, if you take the mass of all the satellites and ratio it to the planet, you see a nearly identical mass ratio. So both Jupiter and Saturn are mostly hydrogen and helium gas by mass. So that tells us that they must have formed when the sun had its hydrogen and helium-rich gas disk, which we think it would have had for the first few million years of its life. This is a hydrodynamical simulation of a gas giant planet growing from such a disk, looking down from above. The brightness here scales with the gas density. If we zoom into the region around the planet, you can see that the inflowing gas, and the arrows here indicate the flow streamlines, has too much angular momentum to fall directly to the planet, and so it instead forms this circumplanetary disk. So as the planet grows, we think it had a hydrogen and helium-rich disk around it. Now, the inflowing gas would have carried with it any small entrained ice and rock particles, and as those particles went into orbit around the planet and collided with each other, they could grow into satellites. So there's an important process that would affect a satellite growing in a gas disk, and it's called type 1 migration. The satellite's gravity induces the formation of spiral density waves in the gas disk, and those are these waves you're seeing here. The back gravitational reaction of those waves on the satellite orbit caused the satellite's orbit to spiral inward and eventually to hit the planet if the migration continues. The rate of this migration is proportional to the mass of the satellite. So the bigger the satellite gets, the faster its orbit decays, and it's also proportional to the gas density, so that as the gas went away, when the solar nebula dissipated, this process would have ended. So I'm going to show you a simulation of satellites growing in such a disk around a giant planet. The simulated satellites are shown by the black circles here. The horizontal line through each one is proportional to the orbital ellipticity of the satellite's orbit. The red stars are the Galilean satellites. As the satellites grow, you'll see them move up this plot. This is showing the satellite mass. And as they migrate inward, you'll see them move to the left until they finally are near the planet and removed from the simulation. So the inflow delivers mass to the disk. Satellites grow, but they only grow until they reach a critical mass at which the time scale for their growth becomes comparable to their time scale to be lost due to this type 1 migration. At that point, they can't grow much more before they decay inward. Ongoing inflow to the disk adds more material, and another generation of satellites grows until it reaches that critical mass and then is lost. The plot on the right shows the total satellite system mass in this simulation as a function of time. It grows initially as the inflow supplies material to the disk, and then it decreases in discrete steps as we lose the big satellites to type 1 migration. And essentially, type 1 migration acts like a negative feedback on the mass that can be held in this satellite system. So it causes the mass to oscillate around a relatively fixed value, which for common disk parameters is comparable to the 2 times 10 to the negative 4 mass ratio we see around Jupiter and Saturn. So what we're really interested in is the last generation of satellites that formed in such a process, because those would be the ones that we survive and probably the ones we see today. So in this animation, we're considering an exponentially decaying inflow with time. And in this case, as the gas inflow to the planet ends and the gas disk around the planet dissipates, the type 1 migration process is slowly turned off and the final satellite orbits can stabilize. So this is an example of a system that after a few million years results in 4 large satellites that are similar in mass and orbital spacings to Jupiter's Galilean satellites. But depending on when the gas inflow to the planet ends, compared to these cycles of satellite formation and loss, you can get very different types of final satellite systems. This simulation shows the same basic conditions, and you can see here initially there's 4 large inner satellites that are just about as big as Titan, that's represented by this star here, and 1 large outer satellite here. But in this case, the 4 inner large satellites are lost just as gas inflow to the planet ends. So the final system in this case just has 1 large satellite, a Titan-like analog. This is interesting because it can not only explain why a planet might end up with only 1 large satellite, even though it had a broad disk around it, but it also offers a potential means to produce the rings of Saturn. If a very large satellite, say the size of Titan, which is comparable in size in mass to our moon, as such a large satellite forms, it seems probable that its ice would have been heated to the point of melting. And once that happens, any rock that's in the satellite will rapidly coalesce into a rocky core in the center. As a large satellite that has a rocky core and an icy mantle spirals very close to the planet's tides will tend to strip off the icy outer layers of the satellite and form a massive icy ring, while the rocky core, by virtue of its much higher density, can maintain its stability until it ultimately hits the planet. So in this way, the same process that could be responsible for why Saturn doesn't have an inner large satellite currently may also be responsible for the creation of its massive icy ring system. So to conclude, the process of giant impacts can produce a very broad diversity of satellite systems similar to those we see around the solid planets and dwarf planets. And it's possible that the formation of satellites in gaseous disk around growing gas giant planets will naturally select for a common satellite system mass ratio similar to that seen in our solar system. And this may actually be a testable prediction in the future as we become able to observe or at least place limits on the properties of satellites around extrasolar giant planets. Thank you.
Of the Earth, starting with my talk. I'm going to be talking about the formation and properties of planetary moons. Our solar system, of course, is host to a large and diverse population of planetary satellites. Around the inner planets, the inner solid rocky planets, the most well-known satellite is, of course, our moon. But Mars also has 2 very tiny satellites, Phobos and Deimos. Around the gas giant planets, we find systems of satellites. These include some very spectacular individual objects, including icy Europa with its subsurface ocean at Jupiter, and Enceladus at Saturn, which we now know to be a geologically active object that is venting water-rich vapor plumes through geyser-like structures near its south pole. Moving out beyond Neptune, there's a population of so-called dwarf planets, including Pluto, but there are other large objects as well, and some of these are now known to also possess satellites. So we'd like to understand the distribution of these objects and how they formed, because, for one, they provide constraints on how our planets themselves formed. But also more broadly, we'd like to understand what this distribution of objects may tell us about the potential for moons in other planetary systems. So in recent years, the Kepler Space Telescope has identified thousands of exoplanets orbiting other stars by detecting the small decrease in the light from the star as the planet passes in front of the star, a transit event. The Kepler exoplanets are shown as the yellow circles on this plot that shows the radius of the planet in Earth radii as a function of its orbital period about its host star. The Kepler mission was designed to identify Earth-like planets, those with solid surfaces that could hold on to an Earth-like atmosphere for billions of years. And it's found many planets comparable in size to the Earth, but perhaps more surprisingly, it's identified a population of gas giant planets on very Earth-like orbits. Planets that are probably similar in structure to the gas giants in our solar system. And in these systems, if we're interested in an Earth-like planet, the place where you would look would potentially be as a moon of one of these large gas giant planets on an Earth-like orbit. So I'm going to start with a very simple plot that shows properties of the satellite systems in our solar system. In blue are the satellite systems around the solid planets and dwarf planets. In orange, the satellite systems around the gas giants. So what I'm showing here is the mass of the whole satellite system ratioed to the mass of the planet as a function of the absolute mass of the planet in Earth masses. So around the solid planets, we see a very wide diversity in the relative size of moons compared to their host planets. The Pluto-Charon system is one extreme, with Charon containing more than 10% the mass of Pluto. And the two small satellites of Mars contain such a small fraction of Mars's mass, they don't even fall on this plot. In contrast to that diversity in relative masses, around the gas giants, we see nearly a constant satellite system mass ratio of order 10 to the minus 4. And so we'd like to understand at a basic level what could have given rise to these two different types of populations. So we think there are at least two processes, there are more also, that are effective producers of satellites. One most relevant for solid planets, the other for gas giants. Starting on the right, during the first few million years of its life, the Sun was surrounded by a gas-rich disk, primarily hydrogen and helium gas by mass. And the gas giants were able to capture some of that mass because they grew to sizes large enough before that disk dissipated, to sizes of order 5 to 10 Earth masses, and at those masses they were able to gravitationally hold on to some of that hydrogen and helium gas. As the gas inflows to the planet, it tends to form a disk around the planet, which is a natural site for satellite formation. Now, the terrestrial planets and the dwarf planets never grew that large. Instead, we think the final stages of their formation were dominated by large impacts between other solid planet-sized objects. And so I'm going to start by talking about this mechanism of satellite formation. And the most work on this particular mechanism has been done in the context of our moon, which, as Frank mentioned, is one of the oldest questions in planetary science. So the moon contains about 1% of Earth's mass. It orbits at a distance right now of about 60 Earth radii from the Earth's center. But it hasn't been there. Its orbit has evolved substantially over its history. Tides raised by the moon on the Earth and the interaction between the moon and those tides leads to a transfer of angular momentum from the Earth's spin to the moon's orbit so that the Earth slows down and the moon's orbit expands over time. That process conserves angular momentum so that we know when the moon first formed, it was very close to the Earth and the Earth was spinning quite rapidly with only about a 5-hour day. So the idea that the moon was formed from a giant impact with the Earth was first proposed in the post-Apollo era. The idea was that a large off-center collision with Earth and another planet-sized object delivered the angular momentum necessary to give Earth that 5-hour rotational day. And if debris from that collision was ejected into orbit around the Earth, the moon could then later accumulate from such a disk. So in order to try to model these types of collisions, there have been decades of work devoted toward developing ever increasingly sophisticated three-dimensional hydrodynamical simulations of collisions. the commonly used method that I show here divides the impacting planet on the upper right and the target into typically hundreds of thousands to millions of individual particles, and the individual evolution of each particle is then tracked in time as it gravitationally interacts with all the other particles and responds to compressional heating, including phase changes during the impact event. So there's currently active debate about the exact nature of the moon-forming impact that can best explain the Earth-Moon features. This is one candidate that involves a Mars-sized impactor. So you'll see in this animation the impacting planet, shown in the upper right, will collide with the Earth. In the first few hours after the collision, the impacting object is destroyed. In this particular case, part of the impactor recoalesces gravitationally into an interior clump that will soon recollide with the Earth. There's the recollision. And an outer clump passes close to the Earth's surface and is disrupted. So after something like 24 hours of simulated time, you're left with an Earth rotating with about a 5-hour day, and it's surrounded by a disk that contains enough mass and angular momentum to later, we estimate a few hundred years later, accumulate into the Moon. So this is an animation in 3D of the same impact simulation, and it'll give you a sense for the global scale of this event, the effect on the very figure of the Earth, and also the heating of the material by the impact. I call your attention to the color bar here. Red corresponds to fully vaporized rock at low pressures. There's the shock wave on the Earth generated by the impact. There's the re-impact coming of the inner clump. Our viewing point in this animation is slowly changing. So we're moving into the plane of the disk around the Earth. You can see the Earth is very oblate. It's rotating very quickly at this point. Now our viewing point's moving under the planet, looking up, and there's the outer clump as it passes close to the Earth and is disrupted. So we use these types of models to study in particular what can best give us the Earth-Moon system, but also more generally to learn how impacts can produce moons. So in this animation, I've mapped the final state of each of these particles as a color onto the end state of the simulation. So the yellow particles are those that end up in the disk, that could form the satellite later on. The blue particles are those that end up in the planet, and the red particles are those that, escape. So preserving this mapping and running the simulation backwards, one finds that in these types of collisions, it's often the case that most of the material that ends up in the disk originates from a single region of the impacting planet, the yellow particles here. And it's this region that's most effectively torqued into bound orbit through gravitational interactions with the distorted figure of the Earth and the impactor in the hours right after the initial impact. Now, because for many of these collisions, the material that produces the satellite comes from a single region of the impactor that grazes past the target, one finds that as you increase the relative size of the impactor compared to the planet, you produce relatively more massive disk. Conversely, if you decrease the relative size of the impactor compared to the planet, you put less material into orbit. For low velocities, the same is true as you make the impact more grazing. As it becomes more oblique, you tend to make more massive disk. So what this implies is if you imagine a natural variation in the types of collisions that would have happened in the final stages of planet formation, you would have produced satellite systems with very different mass ratios. So on the left is an extreme case of an impactor that's almost as large as the target itself. This particular case is an impact that can produce a Pluto-Charon type system with a very large mass ratio between the satellite and the planet. Conversely, on the right is a much smaller impactor. It's still a giant impactor, and it produces a disk, but ultimately a much smaller satellite relative to the planet. So we think these physical collisions, when it comes to forming satellites of solid planets, offer a good explanation for the diversity of systems that we see in our solar system. So let me now turn to the satellite systems around the gas giants, and I'm going to focus on Jupiter and Saturn in particular. So Jupiter, of course, we have the 4 very famous Galilean satellites. They're on nearly circular coplanar orbits. If you take their mass, you sum all their masses, you ratio it to the mass of Jupiter, you get a mass ratio of 2 × 10⁻⁴. At Saturn, we have a system that looks very different. Big ring system, lots of small and intermediate moons, only one large satellite, in this case, Titan. And yet still, if you sum up the mass in all of these satellites and ratio it to the mass of Saturn, you get nearly the same mass ratio, 2.5 times 10 to the minus 4. So I mentioned earlier that the gas planets acquired their gas as gas inflowed to the planets from the circumsolar nebular disk. Now, as this material flowed into the planet, it had too much specific angular momentum to fall directly to the planet. And so it would instead form a circumplanetary disk around the planet. So this disk would be composed primarily of hydrogen and helium gas, but would also include any small entrained rock and ice solids. So the picture is, viewed here on edge, that we had a gas-rich disk around these planets within which the rock and ice particles would orbit, mutually collide, and grow into satellites. Now, as satellites grow within a primarily gaseous disk, there's an important mode of interaction between the satellites and the disk that takes place. So this is an animation showing the gas density of a disk. We're looking down from above as it's perturbed by a roughly Galilean-sized moon. So the moon perturbs the disk, and these perturbations propagate as spiral density waves. The spiral wave pattern, which is then non-axisymmetric, exerts a torque on the satellite orbit. And this torque is actually negative, so it causes the satellite's orbit to spiral inward towards the planet. Now, the rate at which the satellite spirals inward is proportional to the mass of the satellite. The bigger the satellite, the faster its orbit will decay or migrate into the planet. And it's also proportional to the density of the gas disk. And this mode of interaction is well known, and it's known as type 1 migration. So I'm going to show you some results from a model that's trying to mimic this basic situation where you're forming satellites around a gas planet whose disk is being supplied by an inflow of gas and small solids. The model is tracking the orbits of the solid particles around the planet, and when they collide, it's assuming they merge to form larger satellites, and it's including this type 1 interaction between the gas disk and the satellites. So on the plot on the lower left, the black circles will be the simulated satellites. The horizontal line between each one is proportional to how elliptical its orbit is. As the satellites grow, due to the inflowing mass to the disk, they'll move up the plot and the circles will increase in size in proportion to the size of the satellites. Now on the x-axis is distance from the planet. So as this type 1 migration kicks in, which it does as satellites get large, you'll see the satellites move to the left until finally, when they would collide with a nominal planetary surface near the y-axis, they're removed from the simulation. And the plot on the left is going to show the evolution of the total satellite system mass in this same simulation as a function of time. So the inflow to the disk supplies material. A system of multiple satellites grows. It starts to undergo type 1 migration, and large satellites are one by one lost to collision with the planet. The inflow continues, and a new generation of satellites is formed, and then again lost. Looking on the plot on the right, you can see that this forming and losing of generations of satellites causes the total mass in the satellite system to oscillate about roughly a constant value of order 10 to the minus 4. It goes up as inflow is delivered to the disk, and it decreases in discrete jumps as large satellites collide with the planet's surface. So this model, which is quite simple, gives us a prediction that the total satellite system mass compared to the planet might be a constant value, roughly independent of the total amount of mass processed through this disk. Now, I mentioned that the Sun only holds on to its gas-rich disk for a few million years. The disk then dissipates, the inflow of gas to the planet stops, and the gas disk around the planet dissipates as well. At this point, a final system of satellites can stabilize. So in these simulations, the inflow supply to the disk around the planet is time-dependent. We're concentrating on what the final generation of satellites might look like as a result of this simple combination of processes. In the upper case, you can see as the inflow ends to the disk, the total satellite system mass asymptotes, and we're left with a system of 4 large satellites that's broadly similar to the Galilean system shown here in red. Now, in the bottom simulation, the same parameters are used, except the inflow is assumed to decay with a slightly different rate. So the timing of when the inflow stops relative to these cycles of satellite formation and loss is slightly different. And in this case, you end up with a final system that has one dominant large satellite, a crude analog to the Saturnian system. So these types of models suggest that the similarity in satellite system mass ratio that we see in our system may not be coincidence. There may actually be a physical reason behind it. There's a very new project ongoing that is seeking to find exomoons, moons of exoplanets within the Kepler dataset. This is extremely challenging. They are attempting to detect the signature of a small moon orbiting an exoplanet as this system passes in front of a distant star. Each planet that they analyze takes literally tens of thousands of CPU hours. To date, they have detected no exomoons. However, they've now analyzed many tens of planets, and they've come up with some interesting upper limits for those objects. So their upper limits are shown here as the black triangles. Each triangle corresponds to a different exoplanet and represents at the 95% confidence level that planet does not have a moon at that point or larger. It could have a moon anywhere below that point, or it could not have a moon at all. So an interesting thing to note is that this technique in general is sensitive enough that if large mass ratio satellites were common around gas giants in other solar systems, say mass ratios like that of the Earth to the Moon or Pluto to Charon, they probably would have already detected an exomoon. And in general, this is suggestive that perhaps there may also be a limit on the satellite system mass ratio in other systems similar to what we see. We don't know that yet. We don't actually have any detections, and we don't know where these points will actually fall relative to the values for our solar system. But if we were to suppose that, at least in many systems, similar processes may be responsible for satellite production as in our own system, we can ask, where would be the most promising place to look if one was interested in an Earth-like exomoon? A moon large enough to hold on to an Earth-like atmosphere for billions of years? And the result is shown here in this plot. The most promising region of parameter space to find these large moons would be around very large exoplanets, planets that have several times the mass of Jupiter. Another potential region of parameter space would be around planets several times the mass of the Earth, which, if they had, say, a Charon to Pluto type mass ratio, might have produced a Mars-size or larger satellite through a giant impact. In the next several years, they are going to be able to extend this data set to several hundred additional planets. Hopefully there will be a suite of actual detections of exoplanets, and we'll be able to learn about their distribution. In particular, we're interested in a size range we know little about based on our solar system, and that is objects that fall in between the mass of the Earth and the mass of Uranus and Neptune. We don't have any objects in that size range in our solar system, and yet in the Kepler data set, there are many such objects. And so it seems clear that if we do detect exomoons, we're going to learn something fundamental about the formation of satellites and perhaps planets and their properties in this size range. Thank you.
Существовало несколько теорий возникновения Луны. Самой ранней научно обоснованной теорией была, пожалуй, теория Джорджа Дарвина, сына знаменитого Чарльза Дарвина, который высказал ее в 1878 году. Он предположил, что народившаяся Земля очень быстро вращалась. Под действием центробежных сил планета вытянулась в направлении экватора. Наконец, в один прекрасный день, где-то в районе Тихого океана, отделился огромный кусок Земли, который сделался ее спутником. В 1882 году гипотезу Дарвина горячо поддержал биолог Осмонд Фишер. Отсюда появилось второе название теории Дарвина-Фишера. Она благополучно просуществовала до начала XX века. Этой теории деления противостояла теории захвата, выдвинутой в 1909 году американским астрономом Томасом Джефферсом Джексон Си. Автор утверждал, что Луна сформировалась далеко-далеко в космосе, но однажды, пролетая вблизи Земли, попала в поле ее гравитации и осталась в качестве спутника. Астроном поверил в легенду американских индейцев, будто существовало время, когда на небе Луны не было. Между тем, расчеты показывают, что тело, имеющее массу Луны, пролетающее мимо Земли, не может быть захвачено гравитационным полем последней. Если бы захват все же произошел, то Луна вращалась бы по очень вытянутой орбите. Наряду с этими двумя существовала третья теория аккреции, предложенная еще Кантом в середине XVIII столетия и позже одобренная Лапласом. Авторы предположили, что все тела, включая планеты и их спутники, возникли в силу уплотнения полевой туманности. Их теория на уровне объяснения возникновения всей Солнечной системы просуществовала до наших дней. Изменения коснулись только Луны. Все прочие теории возникновения нашего естественного спутника считаются устаревшими. Хотя и здесь наблюдается широкое разнообразие. Предпочтение отдается теориям, лежащим в рамках катастрофического сценария. Нынешним реконструкторам истории Солнечной системы разонравились медленные, эволюционные процессы. В образах их представлений непременно фигурировали взрывы, и чем больше их, тем лучше. В 1975 году в журнале «Икарус» появилась статья Уильяма Хартманна и Дона Девиса, в которой предлагалась теория образования Луны в результате столкновения прото-Земли с теей. По поводу аккреционной теории, Хартманн писал: «Трудно представить, что два небесных тела вырастают рядом из одного орбитального слоя вещества, но при этом одно из них забирает все железо, а второе остается практически без него». Ему возражали аргументом сепарации, когда тяжелые элементы естественно сосредотачивались в центре максимального завихрения. Сходным образом в этой теории объяснялся и дефицит летучих веществ. Они просто испарялись при столкновении и дроблении кусков аккреционного диска. Как ни старались последователи Канта, их аккреционная теория в отношении Луны потерпела фиаско. Согласно теории Хартманна-Девиса, первоначальным местом пребывания теи была область вблизи так называемой точки Лагранжа. Все тела, находящиеся в этой зоне, ведут себя спокойно, не стремятся ее покинуть. Но дело происходило в ранний период становления Солнечной системы, когда в пустом пространстве космоса летало множество кусков бесхозного материала. Эти куски попадали в поле тяготения теи, прилипали к ней, увеличивая тем самым ее исходную массу. И вот, 4,5 миллиардов лет назад, масса теи сделалась настолько огромной, равной примерно массе Марса, что она почувствовала себя Орфеем. Вышла из своей тихой гавани, то есть точки Лагранжа, и пустилась в свободное плавание. На этом пути тея налетела на Гею, прото-Землю, со скоростью примерно 4 км в секунду. Но не так, чтобы удар произошел прямо лоб в лоб, а под некоторым острым углом, не более 45 градусов. Таким образом, при ударе металлическое ядро Геи задето не было. Зато ее мантия разлетелась во все стороны, образовав аккреционный диск, на который, однако, пошло не более 2% ударившей массы. Основная часть теи превратилась в Вселенную, которая быстро, примерно в течение столетия после удара, превратилась в знакомую нам Луну. В теории Хартманна были учтены плотности вещества двух столкнувшихся масс. Плотность Земли равняется 5,5 граммам на кубический сантиметр. Плотность Луны заметно меньше 3,3 грамма на кубический сантиметр. Это объясняется тем, что Земля имеет железо-никелевое ядро, которое составляет примерно 3% от всей массы Луны. По этой причине, между прочим, была отвергнута аккреционная теория совместного образования Земли и Луны из одного протопланетного облака. Между тем, Луна имеет сходный с Землей изотопный состав кислорода. В этом отношении, например, Марс и астероиды отличаются от Земли и Луны. Только по одной этой позиции можно сделать вывод, что Луна генетически связана с Землей. Правда, Луна и Земля заметно отличаются друг от друга в ином плане. Луна, по сравнению с Землей, имеет низкое содержание легко летучих элементов, таких, как водород, азот, фтор, инертные газы. Напротив, на Луне наблюдается некоторый излишек относительно тугоплавких элементов, в частности, титана, урана и тория. И еще, на Луне нет воды или ее слишком мало. На Земле же воды много, очень много. Когда говорят, что при ударе вода на Луне испарилась, то при этом забывают, что и Земля находилась в тех же температурных условиях.
Dryness of the moon is consistent with the giant impact theory, which predicts that water and other volatile compounds would have evaporated out of the lunar debris cloud. But the moon may not be so dry after all. In 1998, the unmanned lunar prospector began an ambitious mission to map the lunar surface with an instrument called a gamma-ray spectrometer. The data showed that hydrogen is spread widely across the poles of the moon. If it's from ice, millions of tons of water could well be embedded in the soil there. It turns out there are places where water can exist on the moon, where the sun never shines. Polar craters forever in shadow could shelter significant quantities of ice against solar radiation.
Говоря о различном химическом составе лунного и земного базальта, забывают, что речь идет о среднестатистических параметрах. Индивидуальные же отклонения и на Луне, и на Земле существенно выше. Так что перечисленные эмпирические показатели не могут служить весомым аргументом в пользу какой-либо определенной теории. Впрочем, в Википедии пишут, что Луна имеет прочную кору толщиной от 60 до 80 километров, что в несколько раз толще земной коры. Считается, что лунная кора образовалась из продуктов плавления лунной мантии. Очевидно, что первоначально Луна была нагрета до полного плавления. Земля же никогда не была полностью расплавленной. В любом случае, описанная выше легендарная история о Гее, Тее, Орфее и Селене не может быть объектом точного количественного расчета. Так что вряд ли теория Хартманна в чистом виде тянет на всесторонне обоснованную физико-химическую модель. Поэтому, естественно, она подвергалась критике с различных сторон, пока в 1997 году известная нам американская исследовательница Робин Кеннеп не написала диссертацию на тему рождения Луны. В основании своей идеи она положила лучшую на сегодняшний день концепцию гигантского столкновения. Главное расхождение ее теории с исходной состояло в следующем. Робин Кеннеп считала, что вновь сформированная Луна должна оказаться на достаточно нестабильной орбите, поэтому, рано или поздно, она должна упасть на Землю. Орбита Вселенной должна быть скорректирована мощным вторым ударом. Такое представление, разумеется, тоже не было результатом строгого механического расчета. Просто Робин Кеннеп так чувствовала и видела ситуацию. Она представляла себе соударение двух тел, масса которых относится как 1 к 81. Ей казалось, что Хартманн и Дэвис слишком мало оставили осколочной массы для формирования аккреционного диска. В результате второго удара, по ее мнению, общая масса осколков должна возрасти до необходимого объема, при котором произойдет стабилизация системы Земля-Луна. Этот взгляд на вещи выглядит слишком узким, искусственным построением на фоне почти 200 спутников, которые вращаются вокруг 8 планет Солнечной системы. Здесь нужен явно более универсальный подход к планетам и их спутникам. Огромное разнообразие планет и их спутников, как по химическому составу, так и по физико-механической линии, невозможно объяснить видимыми внешними причинами. Тут надо прибегать к эфиру. Всякий раз изобретать для каждого спутника планеты свой индивидуальный механизм возникновения – дело абсолютно безнадежное.